So I just wanted to give a little video that I found, just showing that light is very fast. It also can be very slow as well. If I travel from Leeds to London, it normally takes me about 4 hours to drive from Leeds to London in a car. And if you were traveling at the speed of light, it would take you 1/1000th of a second, which obviously is very fast. And I think to myself, well, if you're traveling at that sort of speed, and I've always thought to myself, well, you can go streaking across the universe, and get to the nearest planet in no time. But this video, you might have seen this on the signals from Perseverance going to Mars, and the signal time to and from Mars at the moment is about 11 minutes, and it's about 20 minutes round trip. This is showing in real time light pulses. Initially, there were quicker light pulses of only about a second, but now they're showing every 5 seconds, and the distance from, and it's in real time, so the distance from Earth to Mars is shown at scale, although the planet and Mars are not to scale, but the distance is. So the light is moving out towards Mars, and this would be Mars at its closest position to Earth. It's a little bit further out at the moment, and it would take, normally it can take, the light pulse would take between 3 minutes and 20 minutes to get to Mars. It might take 20 minutes when Mars is at its furthest away from Earth. So you can see that the light pulse is moving quite slowly across towards Mars, and you think, well, that's not really streaking across the galaxy like you might imagine. And the distance, as I said, is to scale, and the light pulse is every 5 seconds. So it'll take some time to get to Mars, even at its closest position. The launch of Perseverance with Mars was at a lot closer position to the Earth when it launched, and when Mars arrived at Mars, Perseverance was quite a bit further away from the Earth. So if you were traveling across the galaxy to the nearest planet, it wouldn't take you 4 hours to get that to the closest planet. It would be to Alpha Centauri or Proxima Centauri before years before you got there, if you're traveling at the speed of light, or 6 years if you were traveling to Barnard's star. So that's it. I just wanted to show you that light can be travel slowly as well as fast, relative to the distances it's traveling.
Thank you, John. I hope you don't mind me saying it, but you've shown a lot of light on the subject.
I particularly like the light waves going from Mars to Earth, where I don't know, it just seems to be like ominously coming towards us as well.
Yeah.
But isn't it the case, though, that as far as the photon is concerned, there's no time at all?
Well, it has no mass.
No, it's time dilation. At that velocity, there is no time. I used to say in a classroom, you know, this old business about you turn a TV on, or at least in the old days, and a certain proportion of the static is from the microwave background radiation. Well, for those photons that have just arrived, the event that created them It's just happened. So it's another way of thinking about it, perhaps. But a photon, yeah, it's got no mass, and yet it's got momentum. So, you know, how to do that?
I mean that for someone riding on the photon, say, no time at all would have passed since
No.
it was emitted.
No.
Yeah.
That's why relativity really baffles everybody.
Yeah.
Yeah, so it is actually possible to visit these stars, theoretically, even though they're so far away. But as you start to get towards the speed of light, then the time dilation means that you can travel great distances. And it's actually possible. There's a video on YouTube I was watching that's quite interesting about.
Yeah, you turn around at
constant
the far
1G.
end and come back at nearly the speed of light, and you come back and everybody's dead.
Yeah, at least you got to see it.
Yeah.
Yeah, there's this video about constant 1G acceleration. It's quite interesting.
I think most people are probably dead already.
Not about the speed of light, but it made me wonder, when you're trying to get messages to and from the lander on Mars, landers, how much of a window have you got before the sun gets in the way? How near to the sun can you be before you've got to stop transmitting and wait? And what happens to the landers whilst you're doing that?
They'll have it all worked out. They will have known before these things set off what the parameters were for communication. They'd have it worked out, I'm sure.
Well, my youngest son is working on the trace gas orbiter of the ESA ExoMars mission, and something that hasn't been very well publicized is that when Perseverance was landing on Mars, 60% of the image data coming from it was being beamed back to Earth by the ESA trace gas orbiter, because NASA didn't have the means of transmitting back the images itself, because their spacecraft wasn't in the right position.
I think what people tend to forget is that, like as Dave has just said, there is quite a lot of orbiting probes and what have you going around Mars now that they can use as secondary communicators from the surface or from something coming in. It's quite interesting that they've now got this network of quite a lot of hardware up there orbiting around that they can use.
Yeah, and it's good how, when you look into it, just how much international collaboration there is on it. So it's all dependent on whose spacecraft is in the right position to pick up the signals from the surface and beam them back to Earth at any one time. They're all coming forward to help at different junctures.
It's okay to account for the spin of the planet and the spin of the Earth, but there's still no answer for what happens when it goes around the back of the sun, unless you've got some other spacecraft which is well away to an angle.
Well, I imagine there is a signal blackout. There's certainly,
there must be, yeah.
As Mars is going further away from us, the bandwidth that's available for transmitting signals back to the Earth is diminished. So there's definitely a reduction in the data coming back from Mars as Mars goes further, well, as it goes into to the other side of the sun, until there's complete blackout.
And then you've got this time difference, like John was showing with that video of, I think on average something like 12 minutes, isn't it? Is it 12 light minutes?
Oh, to get there, yeah.
And then you've to respond back again, it's another 12 minutes, or 24 minutes. On average, it'll vary depending on how distant Mars is. which varies during the course of the two planets' orbits. But it's about that, and so they have to allow for this gap, you know, between receiving and responding.
Well, the answer to the original question is there's a 2-week gap from June the 7th to June the 21st. Mars will be behind the sun from Earth's perspective, and there'll be no communication during that time. That's on the space.com web.
Very much. That's not as long as I thought.
Hope I can, this isn't, thanks Steve, this is not a scientific thing. I just thought before we finish, I watched a program the other week about one of my heroes, Groucho Marx, and in one of his films talking about going around the back of the sun, and he's kissing this lady and she says, closer, closer. And he says, if I get any closer, I'd be around the back of you. Thought I'd tell you that, sorry.
Right, well,